On October 16, 1846, at Massachusetts General Hospital in Boston, a dentist named William Morton placed a glass inhaler over a patient's face. He pumped in ether vapor. The patient went unconscious. Surgeon John Collins Warren made an incision into the patient's jaw. The patient did not move. Warren looked up at the audience in the surgical theater and said, "Gentlemen, this is no humbug." That was the first public demonstration that human consciousness could be chemically switched off on demand and switched back on. In the 180 years since, general anesthesia has been administered hundreds of millions of times. Every day on every continent, in every major hospital, someone is put under. But for most of those 180 years, nobody had any idea how it worked. Not the anesthesiologist giving it, not the chemist making it. The case is still open. Not sleep, not a simple dimmer switch. A chemically induced reversible coma. Today there are three serious competing hypotheses. None has been proven. The evidence for each is real. The contradictions in each are real. Hypothesis 1 points to lipid membranes. That's the fatty bilayer that forms the outer skin of every neuron. Back in 1901, a scientist named Hans Meyer and another named Charles Overton independently discovered a strange correlation. The more lipid-soluble an anesthetic molecule, the more potent it was. The idea took hold. Anesthetic molecules dissolve into the membrane, disrupt the ion channels that let neurons fire, and the brain goes quiet. It's a simple physical explanation, and it's partly true. But it doesn't explain everything. Some anesthetics don't fit the correlation. And even if the membrane is disrupted, that doesn't explain why consciousness, specifically, vanishes. Hypothesis 2 is more precise. It points to protein receptors. Two in particular, GABA-A, a receptor that puts the brakes on neural activity, and NMDA, a receptor that excites it. Many anesthetics bind directly to GABA-A and enhance its braking power. Some block NMDA, cutting off excitation. The result is a global dampening of brain signals. This explains a lot. Different anesthetics target different receptors, but knockout studies, where scientists genetically remove a receptor, don't completely eliminate anesthesia. The brain still goes down. Something else is happening. And then there's the third hypothesis. In 1994, Nobel Prize-winning physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed something that sounded like science fiction. They argued that consciousness arises from quantum vibrations inside microtubules, nanoscale protein scaffolding inside every neuron, and that anesthetic gases switch off consciousness by entering these microtubules and damping those quantum vibrations. They called it orchestrated objective reduction, or ORCOL. The mainstream reaction was swift and cold: quantum coherence. The delicate synchrony that quantum effects demand was thought to be impossible in the warm, wet environment of the brain. At 37 degrees Celsius, thermal noise should destroy any quantum state almost instantly. In 2000, physicist Max Tegmark published a calculation. Decoherence in microtubules would happen in femtoseconds, a millionth of a billionth of a second. Far too fast for consciousness. The case was considered closed for 25 years. Except Penrose and Hameroff had made a prediction, a testable one. If anesthetics work by damping quantum vibrations in microtubules, then stabilizing those microtubules should make it harder for anesthetics to do their job. You need more gas or more time to switch off consciousness. In 2024, researchers tested exactly that. They took rats and gave them a drug called epithylin B. Epithylin B stabilizes microtubules. It makes them resistant to dismantling. Then they exposed the rats to anesthetic gas. The result, the drug-treated rats took significantly longer to lose consciousness. The timing matched what the Penrose-Hameroff theory would predict. It was not proof of consciousness being quantum, but It was the first direct experimental evidence that microtubules play a role in how anesthesia turns off the mind. Remember that moment in 1846? Gentlemen, this is no humbug. The same question now had a physical lead. Then, in 2025, a team in Oxford published in the journal Neuroscience of Consciousness. They detected quantum behavior in microtubules at body temperature. This directly challenged the decoherence objection that had buried the theory for decades. The paper's conclusion was cautious but firm. The quantum substrate is experimentally supported. The fringe theory now had physical evidence on two fronts. It could no longer be dismissed as mere speculation. The debate is not over. None of the three hypotheses stands alone. What's emerging is that anesthesia is likely a cascade. It hits lipid membranes, it hits receptors, and it hits microtubules, the deepest layer. The one that silences consciousness itself may be quantum. This is where the case file turns into something larger. Peer-reviewed paper in the journal Anesthesiology, the flagship publication of the American Society of Anesthesiologists, argues that understanding anesthesia and understanding consciousness are the same problem. Solve one, and you solve the other. If the quantum microtubule theory holds, then consciousness is not just a computation. It is a physical process happening at the nanoscale inside the scaffolding of your neurons. Right now, and every day in operating rooms, anesthesiologists are turning it off. Tomorrow morning, somewhere in the world, a patient will count backward from 10 and slip into that chemically induced reversible coma. A surgeon will pick up the scalpel. The monitors will beep. The body will not move. The mind will be absent. We still don't know precisely how that absence is achieved. But for the first time in 180 years, the evidence is building. The case is not closed. But the next chapter is being written. Gentlemen, this is no humbug.